So this was the problem that I didn't get to in the Zoom session today that I wanted to go ahead and share with you. Here we have a simple random sample of 81 births of Chinese babies. Results in a mean birth weight of 3,245 grams and a standard deviation of 466 grams. We want to test the claim that the standard deviation of birth weights of Chinese babies is equal to 567 grams, which is the standard deviation of birth weights of Caucasian babies. Use a 0.01 significance level and assume that the birth weights are normally distributed. So I've got a lot going on here. First of all, let's focus on the claims. We want to test the claim here that the standard deviation of birth weights is equal to 567 grams. So our claim is about the standard deviation. So it's going to be a standard deviation type. And then I want to go in and identify the values. So here I have a sample size of 81. And then we have a mean birth weight of 3,245 grams. So this is the mean, and it's the mean that's coming from the sample. So that's going to be an X bar, and the S is going to be 466 grams. It's an S and not a sigma simply because it is coming from our sample. It's coming from the 81 births. Okay, so we're going to be testing the claim about the standard deviation. So the standard deviation that's stated there, that is going to be the sigma that we use in our problem, which is 567 grams. We have an alpha of 0.01 for our significance level. Okay, all right, so as far as our requirement check, we have to know that it is a simple random sample, which we assume that, and then the other part is it has to be normally distributed. This one is normally distributed. They tell us that, so we're good with that. So we're ready to set up our null and our alternative hypothesis. So our null hypothesis, since we're testing the standard deviation type, is going to be sigma equals, and the value that it equals is always going to come from the claim, so that's going to be this 567. Okay, so our claim is that it is equal to that, so our alternative is going to have to be the does not case. And this is actually going to be our claim statement here. Okay, this is the one that states in symbols what our claim says in words. Okay, moving on to our test statistic. We're going to use the chi-squared test statistic, and that's going to be n minus 1 s squared over sigma squared. So n minus 1 will be 81 minus 1. Our S is 466, square that. And our standard deviation is 567, and we'll square that. So this gives us a test statistic of 54.038. So now we're ready to find our p-value. Remember, for the standard deviation ones, we're using a chi-square distribution that's skewed. So on this one, we're going to need to decide which side to put it on because it's a two-tailed test. So if I look at my chart, okay, so if I look at my table A4, which is the chi-squared table, and I look at 80 degrees of freedom, then what I'll see is this test statistic actually fits more on the left side with the values than it does on the right side. So I'm going to place it here on the left side, and I'm going to find the left tail. So I'm going to do chi-squared CDF from 0, remember these start at 0, to 54.038, and that's going to be with 80 degrees of freedom. Okay, so we're going to get 0.0115. Okay, and it's a two-tailed test, so remember we also have an equal area over here. So I need to double this. So when I double it, I get 0.023. And that is going to be greater than the 0.01, which is the alpha. Okay, so this is my p-value that I'm going to compare to my alpha. So the p-value is larger than the alpha, so my conclusion should be that I fail to reject the null hypothesis. Okay, so here's my null hypothesis, which is also my claim. So I'll say there is not sufficient evidence to warrant rejection of the claim. And you can insert your claim in there. So there's not sufficient evidence to warrant rejection of the claim that the standard deviation of birth weights of Chinese babies is equal to 567. Okay, so our data did not allow us to throw out that way of thinking and think in a different direction on that. So a couple things. This is one of those you have to be careful that you put the test statistic on the right tail. You can use your chi-squared chart as a guide for that, because when I looked at the degrees of freedom being 80 and I looked across that row, then I could see that this 54.038 fit more within the left side than it did the right side. If I had messed up and put it on and found the right tail over here, then what would happen is my p-value would have come out to be more than 1, and that can't happen. So that would be an indication that I chose the wrong side. So just be careful on these two-tailed chi-squared tests. That's the only ones you have to worry about it with, that you watch for a p-value being too much. And if it's more than 1, then you've put it on the wrong side. Okay, so I just wanted to include this so you can have this for reference. If you are interested in any other problems, we did some practice problems for the proportion and for the mean type that were in the Zoom sessions that can be found under the cloud recordings on Zoom on Canvas. So consult those if you'd like some additional practice with those.